Hello dear students, welcome to Tejama YouTube channel. So in this video, I am going to teach you different topics from the chapter work power energy. I have made a PPT, through that itself I will be teaching. So this video will be brief explanation for different concepts from this particular chapter. So without wasting time, let us start the chapter. So welcome you all. So here you could see some of the pictures where the different things are happening. Let me show you them first. So here a whale is jumping out of the ocean. So then here we have the people working and they're carrying some sand from one place to another place, and they're just throwing them at one particular place. And here a person, a warrior or a very energetic person, is trying to push the stone. And here there is one more worker, construction worker, who is lifting a wooden thing. So all of them are doing one or the other work, and they are applying force and they are using their energy. Okay, so from this you could get a sense that we are going to discuss about work, and then it is about energy to do work, and after that it's the power. Okay, so by utilizing energy we do work, and in how much time they are doing that work will be calculated by using this power. Okay, so let us start the first concept, that is called work. So first of all, what is work? So here you can see a student, or a kid who is pulling a toy by using a thread. So he is doing some work. So in general, work is defined as force into displacement. Here I have given work is said to be done. Work is said to be done when an external force displaces an object through a distance. Okay, so if you displace an object, let us consider here I have a water bottle. Okay, if you displace this from here to here by using a force, okay, by using a force, if you displace it from here to here, so this displacement by the application of force gives you the work done. Okay, so then work is a scalar quantity. Here I'm giving some points regarding this work. You can take note of it. Then SI unit of work is joule or Newton meter. Okay, then dimensional formula for work is here dimensional formula for work is m1 L2 t power minus 2. Then the area under force versus displacement graphs gives you work done. This is very important one. So the area under force versus displacement graph, if I plot a graph of force versus displacement, and if I get a graph like this, and if you find what is that area under this area gives you work done. Okay, that is calculated by multiplying force with the displacement. Okay, so this is very important for 1 mark, especially for board examination. Then we have work done by an external force is equal to energy transferred to the body. Okay, so how much energy is transferred to a body, that much work will be done. So if you don't have energy, if you don't transfer energy, so there will be no work done. Okay, there are different types of energy, like chemical energy, kinetic energy, potential energy, okay, thermal energy, wind energy, hydroelectric energy, chemical energy. So there are many different types of energies, but here we mainly talking about the mechanical energy. Okay, so in this chapter we mainly focus on mechanical energy. So how the mechanical energy will be transferred to object, and we make the things to work. Okay, then work done can be positive. Okay, work done can be positive, and it is zero as well as negative. How can work done can be negative will be discussed in the future slides. Next we have component of force. Let us consider here I have an object, and force vector is represented like this. represented by A. So what is the component of A along x-axis? This is x-axis. And what is the component of vector A along y-axis? Component of vector A, it may be force or pressure, whatever it may be, vector A along x-axis and y-axis. So especially here I have taken force, we'll discuss about that later, but here you should know. So let me take angle theta, any one side, this side or this side. So which side you have taken theta, that side will get cos theta. So we can write here vector A into cos theta. Another side you will get vector A into sin theta. Why? Because this side, if I take these two are perpendicular, the total angle will be 90 degree and this remaining angle will be 90 minus theta. So you get actually A cos 90 minus theta. That cos 90 minus theta is called sin theta. Let me show you one more picture here. Look at this. Here you have theta with the x-axis made by the vector B. So that's why you get B cos theta this side, and this side you have 90 minus theta, so you get sin theta. So you should know which side you have theta, that side will get cos theta, and the other side it is sin theta, and these two directions should be perpendicular to each other. Okay, then we have one more thing, that is vector product of two vectors. See, in vector product we have two types. Before that, let me tell you one thing. So if a scalar multiplied with a vector, what do you get? We get a vector again. Okay, I can give you an example. Let me take 2i cap plus 3j cap minus 6k cap is a vector. It is multiplied by a scalar, that is 2. So what do you get? 2 2s are 4i cap plus 3 2s are 6j cap minus 6 2s are 12k cap, right? So this is vector again. So when a scalar multiplied with a vector, you will get a vector again. So you should know this. Meanwhile, if you multiply a scalar with a scalar again, okay, scalar again, so you will get a scalar as the product. For example, 2 into 2 is equal to 4. So scalar multiplied with a scalar, you get a vector. Vector is represented by unit vectors or normal vectors. Okay, so I mean in general by using the arrow marks. Okay, here there is no arrow mark, there is no vector at all, it is just the value. So multiply that, you will get the scalar again, or the magnitude. But when a vector multiplied with vector, you get two cases. Vector multiplied with a vector, there are two cases there. You may get scalar as the product or vector as the product. So that's why in vector product there are two types. One is scalar product as well as, what is that? Vector product. Scalar product means A dot B. This is also called dot product. This is also called dot product. So A dot B is equal to AB cos theta, and vector product, it is cross product. So that is given by A cross B is equal to AB sin theta. Actually you get a unit vector also, n cap. So if you take the magnitude, its value is 1. Okay, magnitude of A cross B, magnitude means value, gives you AB sin theta only, because magnitude of unit vector is 1. This could be asked for 1 mark. Magnitude of I cap is 1, magnitude of J cap is 1, magnitude of K cap is 1. Unit vector magnitude or value is 1. Okay, next we have alternate units of work or energy, because for both work and energy units are same. So what kind of units that we use in general in this chapter are given here. So these are very important for MCQ questions. Okay, so here we have CGS unit, that is 1 erg is equal to 10 to the power minus 7 joule, and electron volt 1 ev is equal to 1.6 into 10 to the power minus 19 joule. 1 kilowatt hour, it is 3.6 into 10 to the power 6 joule, and calorie, which is equal to 4.186 joule. Okay, so all these four units are very much important. You need to remember those values, and this one was asked many times. 1 kilowatt hour is equal to how many joules, and this value 1 electron volt, usually use it in second PUC, especially in electrostatics, very important one. And erg and this one calorie are asked in the previous year question papers very frequently. Okay, so I hope you take the note of this and practice them and memorize them, especially. So memorize them, remember them, they will be useful. Okay, next we have work done by constant force. Work done by constant force. Then we'll consider a situation where a kid is pushing this car in one particular direction by making an angle theta with the displacement, and there is one more situation where a person or a woman is trying to pull the block of wood from one place to another place where she is doing work. So work done is given by what? See, work done by constant force, work done by constant force is the product of component of force along displacement and magnitude of displacement. We have to take, or we have to multiply, means it is the product. It is the product of component of force along displacement and magnitude of displacement, or you can take product of component of displacement along the force and magnitude of force. So let me take a situation where we have applied a force on an object in this particular direction. So where we have force in this direction, so that the block gets displaced from here to here. So you have to take the point of displacement where the force is applied. Force is applied at this particular point, means you have to take that point only from there to there. So displacement is x, or s also you can take. So the angle between those two is theta. So take the component of force along displacement, that is f cos theta. So work done is equal to f cos theta into x. Okay, so this is the formula for work done. Or you can also write force into component of displacement, that is x cos theta, both are same. Okay, so f cos theta into x, or w is equal to f into x cos theta. So in vector form you can write like this, f dot x, because it is scalar product. Here we have cos theta, so we have this here. Okay, this is work done by constant force. So because of this you get unit as Newton meter. For force it is Newton, and displacement it is meter. That's why 1 joule is given by 1 Newton meter. So if you do this much work, this much energy will be utilized. Next we have work done by variable force. This is very special case. So one thing you should know, that we have to plot the graph of variation of displacement when the force is applied. Here the displacement is not constant, or the force is not constant, both are varying randomly. Okay, so variable force is applied, and because of that displacement is also varying, or displacement varies when the force is applied because of different scenarios or different reasons. Okay, how to find the work done? One thing to remember, for 1 mark it is very important. Work done by variable force is calculated by finding the area under force versus displacement graph. So this was asked many times in the previous year question papers, or they can directly ask you, so what does the area under force versus displacement graph gives you? It is nothing but work done. So we just need to find out area under this. So area under this graph Okay, area under this force versus displacement graph gives you work done. Okay, so for that I divide this graph into small sections, small displacements like this, that you can see in the picture here. So the displacements should be so small and equal. So displacement value is given by delta x or dx. You can write delta x or dx, okay, anyone you can take. So area under this particular region here is given by work done. So that is dw is equal to force into displacement. Okay, if you write delta w, we get force into delta x. Let me write dx itself, it will be good for us. So dw is equal to f into dx, small work done will give like that. So we can find the work done for all the component of displacements with respect to force. Then we can find out the total work done by adding them. So what is the work done here? So for force F1, what is the work done here? Force F2. So force is varying. Okay, force is varying, but displacements are same. Displacements are not varying. Okay. So here this is the case, the displacement value is same. So I can find out the work done. Total work done is given by work done for the first displacement delta x by the application of force F1 is given by F1 dx plus F2 dx plus F3 dx plus so on up to like that last one. So there Fn dx. So you can take dx common here. Work done is equal to F1 plus F2 plus so on up to Fn dx. Okay, now W is equal to, if you add all the forces, you get F1 plus F2. Sorry, we have the summation, right? Let me write here. W is equal to summation F I, where I varies from 1 to n into dx. So this is how we can calculate the work done under this particular force. You can also write cos theta if there is the angle between the direction of force and displacement, and you can also represent this in integral form, that is so the displacement is occurring from xi to xf, so it is given by xi to xf fi dot dx, okay, athwa into dx. So this is the integral form of work done by variable force. Okay, next we have kinetic energy derivation, where we have an object. So consider a body or an object of mass m which is already at rest. Rest means its initial velocity is 0. Let the force of magnitude f, okay, applied on the box displaces it through a distance x. This is the displacement. Okay, let its initial velocity is u and final velocity is v and the acceleration is a. You just have to mention what are the terms that you are going to use here. Okay, so I have from equation of motion, what is that? There are three equations of motion. I'm going to consider the second one, that is v square is equal to u square plus 2as. Here, since initial velocity is 0, we get v square is equal to 0 plus 2as. So I need s, that is displacement, that is given by, so what is that, v square divided by 2a. I hope I can write like this. This is equation number 1. Also I know that f is equal to m into a. So you know this, that work done is given by work done is given by force into displacement into cos theta. Okay, here force is applied in this direction and displacement is also happening in the same direction, so theta is 0. So work done is equal to force is how much, m into a, displacement is v square divided by 2a, and cos theta value is 0, cos 0, theta value is 0, so a will get cancelled, cos 0 value is 1, cos 0 value is 1, so we'll get work done is equal to 1 by 2 mv square. Okay, so this half mv square is the expression for kinetic energy. Means what, we have applied force on the object, that's why the body has got some kinetic energy, and that kinetic energy is stored as work done by the body here. So here we can write the work done is stored as kinetic energy in the body. The work done is stored as kinetic energy in the body. Therefore kinetic energy is equal to half mv square, half mv square. Next we'll move on to the new concept. Okay, this is very easy derivation. Similar to that, there is one more derivation that comes under the concept called work energy theorem. So here we have to consider an object of mass m, okay, moving with initial velocity. It is not at rest, it is already moving with initial velocity u. So we have to consider a force of magnitude f acting on it. So that's why it displaces the object through a distance x. So its final velocity will be v and acceleration is a. So here we can make use of equations of motion, that is v square is equal to u square plus 2as. So I take u square to the left hand side, so I get v square is equal to u square plus 2as. So that is v square minus u square is equal to 2as, and I want s here, displacement. So since we have taken it as x, right, sorry, you can write x itself. The previous case itself I have taken s. Sometimes we use x and sometimes you use x. You can write whichever you want. So x is equal to v square minus u square divided by 2a. So this is equation number 1. Meanwhile we have one more case where which is happening on the object, that is force. This is the magnitude of force acting on the object. So if we take the expression for work done, that is force into displacement. So force is given by mass into acceleration. Also you can take cos theta, as earlier theta value is 0 because force is acting in the direction similar to the displacement, so theta is 0. So displacement is given by v square minus u square divided by 2a into cos 0. So cos 0 is 1, so a will cancel out. You are having half m v square minus u square, that is equal to half mv square minus half mu square, that is equal to work done. So isn't it kinetic energy final, because it is final velocity, u is initial velocity, so this is initial kinetic energy. So therefore in general we can write work done is equal to kinetic energy minus final minus kinetic energy initial. So this is called work energy theorem. Okay, so here you have to write statement also. Statement, what is that? Work done by a force on an object is equal to change in its kinetic energy, change in its kinetic energy. So this is the statement, and this This is all about this video, dear students. So I will meet you in the next video, which will be the continuation of this particular chapter. Thank you.